All right, I'm going to work an example of how to use Newton's law of universal gravitation to find the force due to gravity between the Earth and the Sun. To do this, we need to gather a few constants. We need the gravitational constant, g. We need the mass of the Earth in kilograms, the mass of the Sun in kilograms, and the distance between the Earth and the Sun in meters. Newton's law of universal gravitation says that the force of gravity between two objects will be the gravitational constant times the product of the two masses divided by the distance between the two masses squared. Now, even though we have an r in this formula or this law, we do not think of this as a radius. We think of this as the distance between mass 1 and mass 2. So for us, that will be the distance between the Earth and the Sun. Now, with all of these constants and scientific notation numbers and units, I'll be flipping back and forth between a blank white page and this page with all of the constants because everything is going to be very, very wide. So I'm going to start by writing the force of gravity is G, 6.67 times 10 to the negative 11, and then the units here will be meters cubed per kilogram second squared. We'll then multiply this by the mass of the Earth, 5.97 times 10 to the 24 kilograms. And then the mass of the Sun, 1.99 times 10 to the 30th kilograms. This will all be divided by the distance between the Earth and the Sun, 1.5 times 10 to the 11 meters. This will get squared. Now, before I plug all this into the calculator, one of the things I like to do here is make sure all of my units will work out. This is a force, which means it needs to have a unit of newtons, which is a kilogram meter per second squared. So I'm going to run through all of these units. Meters cubed per kilogram second squared times kilogram divided by meters squared. In the numerator, one of the kilograms will cancel with the denominator's kilogram from G. We will have the square of meters in the denominator cancel with 2 of the 3 copies of the meters cubed in G, and we will be left with meters times kilograms divided by second squared. Rewriting that, we can write it as kilogram meters per second squared, which is Newton. So the units will cancel out here, which is beautiful. So now we can go back to typing all of these numbers in with a calculator. 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24 times 1.99 times 10 to the 30 divided by, and here's where it gets tricky. When I type into the calculator my 1.5 times 10 to the 11 meters, and then I want to square, I need to put my 1.5 times 10 to the 11 meters in parentheses, and then have the calculator square that number. The calculator will know to do the square of the denominator before doing the division. So I do all of that to find that the force of gravity is 3.52 times 10 to the 22 newtons. Now I'm just going back into my calculator, making sure that I multiplied by everything correctly. 6.67 times 10 to the negative 11 times 5.97 times 10 to the positive 24, and then times 1.99 times 10 to the 30th divided by 1.5 times 10 to the 11th squared. Now this is a humongous amount of force, and this is mostly due to the fact that the Earth and the Sun are so massive. When we add those exponents together, we get a power of 54. We subtract the 11 from G, 54 minus 11 is 43, and then we will subtract from 43 the 11. So we have a very, 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 very large force, 10 to the 20 newtons.